Hello, hello, hello. Salam. Good morning. It's me again. Now we are going through some computing notations that are used for quantum computing. We're gonna go through the example notations, some fundamental notations, along with their pronunciation, examples, mathematical equations, and code with our good friend Gemini. I will also later check with some other tools. So let's hear what Gemini got to say.
Quantum computing utilizes a specialized set of notations to describe quantum states, operations, and circuits. These notations, largely derived
So we
from
have
linear
here
algebra
qubit
and quantum
states,
mechanics, provide a concise way to
direct
represent complex
notation,
quantum phenomena. Here's an explanation of the most
tensor
common
product,
notations. 1.
quantum gates.
Qubit states. The fundamental unit of information in quantum computing is the qubit. Unlike a classical bit, which can only be 0 or 1, a qubit can exist in a superposition of both states. Computational basis states. Notation: 0 and 1. Pronunciation: ket 0 and ket 1. Explanation:
Ket
these
0,
represent the two
ket
fundamental
1.
or basis states of a single qubit, analogous to the 0 and 1 of a classical bit. They form an orthonormal basis for the qubit's state space. Mathematical equation: vector representation. Example: a qubit in the 0 state is represented by the vector begin, p matrix 1 0, and p matrix. Code example: Qiskit. Superposition states. Notation: psi, pronounced ket psi.
So ket 0 and ket 1 both are column vectors. 1 0 0 1.
Explanation: represents a general state of a single qubit, which can be a linear combination, superposition, of the basis states, 0 and
Superposition state is given by ket psi equals to alpha ket 0 plus beta ket 1.
1. Mathematical equation, where alpha and beta are complex numbers called probability amplitudes. The sum of the squares of their absolute values must equal 1, i.e., alpha squared plus beta squared equals 1 due to the normalization condition of quantum states. Alpha squared is the probability of measuring the qubit in the 0 state, and beta squared is the probability of measuring it in the 1 state. Example: a common superposition state is the plus state, where alpha equals frac 1 sqrt2 and beta equals frac 1.
By the way, these are also called amplitude when transformed into frequency domain.
sqrt2, so plus equals frac 1 sqrt2 0 plus frac 1 sqrt2 1. Mathematical equation, vector representation. Code example: Qiskit. Create a superposition state plus greater than QC equals quantum circuit 1 QCH0 hash apply Hadamard gate to put qubit 0 in plus greater than state. Get the state vector.
So
requires
we need
simulation.
to
State vector
work
equals
with
state vector. QC
circuits
print
in
state
Python.
vector. 2. Dirac notation, Bra-Ket notation. Introduced by Paul Dirac, this notation is fundamental in quantum mechanics and quantum computing for representing states and operators. Ket. Notation. Psi. Pronunciation. Ket psi. Explanation. Represents a quantum state vector in a Hilbert space. Mathematical representation. A column vector. Bra.
Hold on a second. So this is ket psi. This superposition state, it is representing ket psi in a general state of superposition in a single qubit. It is also representing that state vector in a Hilbert space, and mathematically it is a column vector, of course. Let's continue.
Notation. Pronunciation. Bra. C. Explanation. Represents the conjugate transpose, adjoint, of the corresponding ket vector. It lives in the dual space of the Hilbert space. Mathematical representation, a row vector, which is the conjugate transpose of the ket. If equals begin p matrix alpha beta end p matrix, then psi equals begin p matrix alpha caret and beta caret end p matrix, where caret asterisk denotes the complex conjugate. Bra-Ket, inner product. Notation. Phi. Pronunciation. Bra-Phi ket psi, or the inner product of phi and psi. Explanation. Represents the inner product between a bra vector phi and a ket vector, psi. This operation results in a complex scalar. If psi and phi are state vectors, the absolute square of their inner product, phi psi squared, gives the probability of measuring the state, psi to be in the state, phi. Mathematical equation. If phi equals begin P matrix, gamma delta end P matrix.
So hold on. So bracket, the notation is phi, bra phi cat psi. Pronunciation, the inner product of phi and psi. Uh, so we already saw that psi is a column vector. So if I want to calculate inner product, we need bra to be a row vector, which is the case. So phi is a row vector and psi is a column vector. So psi, cat psi and bra psi, they are complex conjugate transpose of the cat, as shown here in the mathematical representation. Anyway, let's continue. So the inner product is given as bra phi cat psi.
Antaeoli. Psi equals begin P matrix, then phi. Psi equals begin P matrix, gamma caret and delta caret end P matrix, begin. Mathematical equared equals gamma caret alpha plus delta caret beta. Example. The inner product of 0 and 1, 0, 1 equals begin P matrix 1 and 0, 1 and 0, 1 and T matrix. Begin P matrix 1 and 0 end P matrix 1, 0 end P matrix equals 1 CDOT1 plus 0 CDOT0 equals 1. This shows it.
Okay, so now we have seen that the inner product bra phi cat psi, it is normalized. Now let's move on to the outer product, which notation is cat psi bra phi. So here cat is first, bra is second, and this, let's hear.
Notation. Phi. Pronunciation. Kit psi bra phi. Explanation. Represents an operator that acts on a quantum state. Mathematical equation. If psi equals begin, mathematical equation, phi is to alpha beta and P matrix, and phi equals begin, mathematical equation, then phi equals begin, mathematical equation, then TeraWorks Realine, mathematical equation, mathematical equation, mathematical equation, mathematical equation, mathematical equation, projection operator onto the 0 state, 0, 0, equals begin, P matrix 1, 0 end, P matrix 1, and 0 and 0 end P matrix. 3. Tensor product.
Okay, so we have this. For example, if we have 0, then we are having. If you have 1, 0 and 1, 0, so alpha psi has 1, 0 and phi also has 1, 0 as its as the vectors, what's representing basically that one of the probability is 1, the other one is 0. So for instance, if we have a superposition of a qubit which is 100% likely to be in state 0, then we will have this 1, 0 column vector as its probability vector. So, and if we multiply these two as outer product, we will get this matrix, 2 by 2 matrix here, 1, 0, 0, 0. Anyway, let's move on to tensor product. So it is this cross symbol with a circle outside, and its pronunciation is tensor product. Let's hear.
The tensor product is used to combine the state spaces of multiple quantum systems, qubits, into a larger state space for the composite system. Notation, circled times. Pronunciation, tensor product. Explanation, used to describe the combined state of multiple qubits. If you have two qubits, one in state, psi underscore 1, and the other in state, psi underscore 2, their combined state is psi underscore 1. Circled times, psi underscore 2, often written simply as psi underscore 1, psi underscore 2, or psi underscore 1, psi underscore 2. Mathematical equation for vectors. If psi underscore 1 equals begin, P matrix AB end, P matrix, and psi underscore.
So this tensor product is different than what we have seen before, the inner product or outer product, where one of the vectors was row vector and other was column vector. In this case, or for the case of outer product, we had like first one is column vector, second one is a row vector. But case is different. They are both column vectors representing two different states, and psi1 tensor product psi2, that is representing uh, the combined state. So let's listen.
Score 2 equals begin, P matrix, CD and P matrix. Then, mathematical equation for matrices. If A equals begin, P matrix A underscore 2, 11, and A underscore 2, 12, A underscore 2, 1, and A underscore 2 end, P matrix, and B equals begin, P matrix, B underscore 2, 11, and B underscore 2, P matrix, P matrix, P matrix, P matrix, P matrix.
Alright, looks like Gemini has some issue pronouncing some of the mathematical equations, but we have got most of the things correct. Now let us gonna move into quantum gates. Let's hear.
Operators that transform quantum states. They are the building blocks of quantum circuits. General gate application. Notation. Oopsie. Explanation. Applying a quantum gate U to a quantum state, psi. The resulting state is oopsie. Mathematical equation. Matrix multiplication of the gate's matrix representation with the state vector. If U is represented by matrix M and psi by vector V, the new state is represented by MV. Common single qubit gates. Hadamard gate. Notation. H. Explanation. Creates a superposition state from a basis state. Mathematical equation. Matrix. Action on basis states H. 0 equals plus equal.
So hold on, let's look at the mathematical equation of Hadamard gate. So H equals to 1 over root 2, 1, 1, 1, minus 1. And action on basis states. Okay.
Frac 1 SQRT2 0 plus 1 H 1 equals frac 1 SQRT2 0 1. Circuit diagram symbol, a box with H inside. Code example, Qiskit, poly-X gate, notation X. Explanation, acts like the classical NOT gate, flipping the qubit state, 0 left right arrow, 1. Mathematical equation.
So we're looking at poly-X gate now. Notation is X. So it flips the qubit state from 0 to 1. Unlike Hadamard gate, which creates a superposition from a basis states. So whether it was at start at 0 or 1, it creates a superposition. For 0, it creates a superposition of 0 plus 1, and for 1, it creates a superposition of 0 minus 1. Alright, let's listen about X gate.
Equation, matrix. Action on basis states X, 0.
So the matrix equation 0, 1, 1, 0. So main diagonal is all 0.
Equals 1x, 1 equals 0. Circuit diagram symbol, a box with X inside, sometimes represented as a circle with a plus sign inside. Code example, Qiskit, poly-Y gate, notation Y. Explanation, a combination of a bit flip and a phase flip. Mathematical equation, matrix.
So poly-Y gate, notation is Y, a bit flip and a phase flip. So here for the first time we also have a phase flip.
Action on basis states Y, 0 equals I, 1. Y, 1 equals I, 0. Circuit diagram.
Minus I0. So Y1 becomes minus I0, Y0 becomes I1. So there is a phase shift here, 90-degree phase shift, and also the value from 0 to 1 and then from 1 to 0.
Symbol, a box with Y inside. Code example, Qiskit, poly-Z gate, notation, Z. Explanation applies a phase flip to the 1 state, leaving 0 and
So Z gate only affect 1 to 0, flip to the 1 state, and 0 remains unchanged. So Z0 becomes 0 and Z1 becomes -1.
changed. Mathematical equation, matrix. Action on basis states Z, 0 equals 0Z, 1 equals dash 1. Circuit diagram symbol, a box with Z inside. Code example, Qiskit. Common 2-qubit gate, controlled, not gate. Notation, CNOT or CX.
2-qubit gate. So controlled, not gate. So C0 or CX. Okay, let's see.
Explanation. A 2-qubit gate where the first qubit is the control and the second is the target. The target qubit is flipped, not if and only if the control qubit is in the 1 state. Mathematical equation, matrix in the basis, 00, 01, 10, 11. Action on basis states, C0, 00 equals, 00 CNOT, 01 equals, 01.
So action on basis states, 00 remains unchanged, 00, 01 remains unchanged, 01 because the control is 0, and 10 becomes 11, 11 becomes 10, so because the control is 1, so it is changing from 0 to 1, 1 to 0 when the control is 1.
Circle on the control qubit line,
A circuit
connected by a
diagram is a
vertical line
plus sign.
to a circled
It is
plus
kind of
sign,
like
circled
same
plus on
for
the target
the
qubit line.
Same for the tensor product, but it is different because it is shown in the diagram. Circle plus sign. Anyway,
Superposition collapses to one of the
measurement is
basis
important.
states, 0 or 1, with a probability determined by the square of the amplitude of that state.
so the qubit superposition collapses when the measurement is done, and it collapses into one of the basis states, 0, 1, 1, with a probability determined by the square of the amplitude of that state.
Notation in circuit diagrams, a meter symbol connected to the qubit line with an arrow pointing to a classical bit line. Explanation indicates that a measurement is performed on the specified qubit, and the outcome, 0 or 1, is stored in a classical bit. Mathematical concept, Born rule, for a qubit in the state, psi equals alpha, 0, plus beta, 1, the probability of measuring, 0 is, alpha, squared, and the probability of measuring, 1 is, beta, squared. After measurement, the state of the qubit collapses to the measured state, 0 or 1. Circuit diagram symbol, qubit, greater than, meter, greater than, classical bit. Code example, Qiskit. These notations form the basic vocabulary for describing and working with quantum information
Alright,
and
that's all we
computation.
have from Gemini.
Understanding them